Right now, you feel perfectly still, but you are strapped to a rock spinning at over 1,000 miles per hour at the equator. You don't feel dizzy for the same reason you comfortably sip coffee on a smooth flight. Everything on the planet's surface, the oceans, the atmosphere, the buildings, and you, is moving together at the exact same constant velocity. But consider what would happen if that invisible physical engine suddenly broke down and the planet slammed on the brakes. This spin provides the structural framework for our climate, geography, and gravity. Breaking it unleashes the raw physics of the universe against us. Let's examine a sudden halt, bringing the planet to a standstill in exactly 1 second. According to Newton's first law of motion, objects in motion stay in motion unless acted on by an outside force. So if the bedrock suddenly locks into place, anything not anchored deep into the crust continues moving eastward at full rotational speed. The atmosphere keeps moving, instantly generating a supersonic windstorm. We're talking about air currents 3 times stronger than the most violent hurricane on record, powerful enough to flatten global infrastructure in moments. Water has immense mass, and its momentum carries it forward too. The world's oceans immediately surge out of their basins, transforming into global mega-tsunamis that wash deep into coastlines and swallow entire territories. Beneath the surface, the sudden deceleration forces the Earth's internal layers to grind against one another. The immense friction between the solid mantle and the molten core triggers global earthquakes and widespread volcanic eruptions. There is exactly one geographic location where you might survive this initial kinetic blast. Researchers stationed here, at the South Pole, have an effective rotational velocity of 0, meaning they wouldn't be flung eastward. For everyone else, the violence of that kinetic energy wipes the surface of the Earth clean of human civilization in 5 seconds flat. What if we take away the kinetic shock? Imagine instead a gradual slowdown, taking 5 full years to coast to a complete stop. This removes the instant violence, but introduces a slow geographic threat. Looking at this cross-section of the Earth, notice the outward push at the equator. The planet's spin generates centrifugal force, pushing oceanic water and atmospheric gases outward. This creates and sustains a massive bulge against the inward pull of gravity. As the rotation slows, that centrifugal force weakens. The baseline pull of gravity forces the equatorial bulge of water and air to migrate north and south toward the poles. This migration slowly drowns the upper and lower hemispheres. Vast swaths of North America, Siberia, and historic cities like London would become the floor of a massive, deep polar ocean. Back at the Earth's middle, a geographic inversion takes place. As the water drains away, the newly exposed seafloor connects the existing landmasses into a single, dry, continuous equatorial megacontinent. But surviving on this new supercontinent presents a critical problem. The atmosphere follows the water to the poles, leaving this equatorial landmass with air too thin to sustain human life. The air pressure at sea level here would mirror the deadly, low-oxygen environment we currently see at the extreme outer limits of human endurance. Altitudes where climbers require oxygen masks just to take a step. Furthermore, a completely still Earth remains locked in its orbit around the Sun. Our days stretch into annual cycles, exposing the surface to 6 continuous months of blistering sunlight, followed by 6 months of freezing darkness. Then comes the final blow. Without the planet's rotation, the internal iron core stops spinning. The Earth's magnetic shield collapses, allowing solar radiation to directly bombard the surface. A gradual stop prevents instant kinetic death, but it guarantees extinction by drowning, suffocating from thin air, freezing in endless darkness, and irradiating whatever life remains. All of this is hypothetical, of course. Yet the Earth's rotation actually is slowing down right now, driven by the subtle drag of tidal friction caused by the Moon's gravitational pull. The scale, however, is microscopic. The deceleration amounts to roughly 1.7 milliseconds every century. We track this minute delay using highly precise atomic clocks, occasionally inserting a leap second into our calendar to keep global technology and navigation perfectly synchronized. At this current pace, it will take billions of years for the Earth to halt entirely, an event slated to occur long after our sun burns out. Earth's rotation holds our oceans, atmosphere, and magnetic shield in place. This constant motion is the physical foundation that keeps the planet habitable.